will record here. It is now recording, so I will start. So as I mentioned, this is a review session, a first review session for exam number 1. I will go ahead and start talking about or listing the number of topics that we will cover in the exam. Obviously, everything that has to do with the mobility of electrons, so the drift velocity, the mobility, the conductivity of the materials, resistivity, the way resistivity or conductivity is calculated, what is else? Yeah, the current density, the current, and all these parameters. Okay, so this is the first one. So basically, it's really some basic electronic or electrical properties of materials that we calculated from the treating the electron as a particle. Then another thing, obviously, we then did several problems. So we'll do this problem, the hydrodynamic electron flow. So where we started treating the electron as a flow of fluid that is getting an acceleration due to the force, the electric force, but also that is getting a friction due to the collisions with the atoms or the molecules of the material. And then we developed this hydrodynamic model. Then one of the most this is a big part, okay? And another big part will be the Hall effect. So if the exam, for example, will get 3 or 4 problems, definitely there will be a problem here, or a mixture of both of them. I will show you in one of the problems on all the exams what I did. So the Hall effect. The Hall effect, obviously, sometimes I might ask you to calculate the Hall coefficient, the Hall electric field, and the potential, and obviously the direction of motion when we apply the magnetic field. Then we started the electromagnetic waves, or the propagation of the electromagnetic waves in solids. And for that, we derived the Maxwell's equations. Obviously, I will not give you the derivation of the Maxwell's equations, but what is very important is the dispersion equation. So dispersion equation, I will show you in the exam that the list of formula that I'm giving, and also I will post those exams so that you know which formula are given. Dispersion equations, and the dispersion equation, it's very important to understand its meaning, as I explained in class, when there is a dielectric and when sigma is different than 0, and when sigma is very large, which means when sigma is very large, then which means it's purely conductor, is a very high conductor, conducting material. And then obviously what will happen is that the real part will be very, very small compared to the imaginary part, and then the dispersion, the wave number, will be a few full imaginary part. And obviously how the dispersion equation is related to the attenuation of the wave in solids, in conductor, attenuation of waves of the wave, and how to calculate this attenuation. We will give problems. And obviously, we calculated in the same propagation of electromagnetic waves in solids. We calculated the skin depth, and the skin depth is related to the wave frequency and the material, the permeability of the material, and also the conductivity of the material. Okay. Yes, so here, for example, we'll tell you, okay, might ask you to calculate the skin depth of a material given different wavelength or frequency of the waves. Yes, and the other thing, how the resistance of the material is changing. The resistance of the material is changing. If you remember, the resistance of the material when this material is used to conduct or to transmit an electromagnetic waves, then it is of the order of the resistivity, the intrinsic resistivity of the material divided by 2 pi the cross section. So the cross section, this is the cross section. For example, if I have a copper wire, and this is its cross section, because of the behavior of the propagation of the waves in the material. So the wave is propagating in a thickness delta, which is the skin depth, and then the resistance of the material becomes the resistivity, intrinsic resistivity divided by 2 pi a, and then the skin depth. Okay, so this is a very important quantity. And I think we did an example yesterday, no, the day before on it. Okay. Then the conductivity, yes. So this is very important, the conductivity. If you remember, we calculated the conductivity is also changing, but the conductivity of a material is changing when the material is used, or the conductor is used to transmit a wave, and the conductivity, we have seen that it's equal to sigma 0 over 1 minus I omega tau. And this is the intrinsic conductivity, which is the DC conductivity when there is no electromagnetic wave propagating through, or no AC current or AC wave propagating through the material. And this is the collision time, or the relaxation time. And obviously, we also defined the real and imaginary part. Okay, and please, this is what I mentioned to you, when I ask you calculate the conductivity at a certain wavelength, this means I'm asking you to calculate the magnitude of the conductivity, which is sigma 0 over the square root of 1 omega tau squared. Or sometimes I might ask you, what are the real and imaginary part of the conductivity? And again, I explained to you last time that this sigma, if you do the calculation, you will be able to find the real and the imaginary part of the conductivity. And finally, what we did, we calculated the power. We started from the fact that the power is V squared over R, and we start also the fact that the resistance of this is the resistance, and the resistance is equal to L, the length of the cable divided by its conductivity times the area, the cross section, and also the electric field that is used in the wave, that is applied to the material, and the electric field is equal to the potential difference divided by L. And we have demonstrated that when we apply all of this, we obtain what we call the volume power, which is the power divided by the volume, which is equal to sigma omega squared, so sigma E squared. Now, sigma obviously is sigma of omega E squared, because sigma now is changing as a function of the frequency. Okay, so this is really, and obviously here, because sigma volume, no, the power, the volume, the power volume, or the power per volume is equal to sigma. And since sigma has a real part and imaginary part, the power will have also a real part plus an imaginary part that you might be asked to calculate in certain applications. Okay. Any question? Can you send us this note? Okay, well, Well, look, but you can, I'm recording the session, so I will just put it on the web and I will send you the link, and then you can, I mean, it will be easier for you because then you have the note and you have yeah, you have the note and you have my voice also. If you don't like the voice, then just mute and look at the formulas. Yeah, so there was a question how to calculate the imaginary part. Well, look, let's say this is the power per volume. I said that it's equal to sigma omega and E squared, right? So obviously, sigma omega has it's equal to sigma real plus I sigma imaginary, which we already calculated, times E squared. Now, this will give you sigma real times E squared. Now, E squared is a real, even though this is a magnitude of E squared. So the magnitude of E will give you a scalar, a number, okay? It's not a vector. So this one is a real part, plus I or J, I sigma imaginary times E squared. So this is the real part of the power, and this is the imaginary part of the power. Okay. Okay. Any questions? Okay, if not, now I will start solving one exam. So that is an exam. I think that the exam. Yeah. So this is the exam. I think. See, I always have this problem with this OneNote. Okay, so this is an exam that what is this? What will come in your is this, what I just mentioned. In my note, it's chapter 1. In my note, the note that I put. Yeah, okay. Okay, let's first continue with this. I will try to yeah, so if you look at my note, those are chapter 1. As I mentioned, I told you before, usually historically there were a textbook, but it was horrible. Everybody was complaining, and I honestly I don't consider it. It's a very, very good book, but it was not really a textbook that is dedicated to students. I mean, a textbook where you have examples that can be solved, where you have applications. That was not really a textbook. So when I took over this course, I chose another textbook, and then I combine both of them and produce my own note, and I am giving you the note. So that's why it just because in the new textbook, there are several things that you would not need, and several things that are very elementary. So that's why for example, in the new textbook, they would start solving Schrodinger's equation chapter 2, chapter 3, as we did in Physics 222. We already did this. I will not repeat again everything about discussion, whether it is a wave or not. This we have already done in Physics 222. So that's why I produced my own note, and I already give you the note for the full chapter 1. And once we start chapter 2, I will give you again. Now let's focus on this chapter, which is a long chapter, by the way. So this is an exam, and you can see those are the formulas that you will have. Yes, so here you have the usual formula, the thermal velocity, electron mobility. Now, I'm not giving all the formulas because some of the formulas you can figure out yourself. For example, we all know what is the relationship between the current density and the current. right? I will not give you this formula, but I'm just giving you, for example, what is the relationship between sigma and the number of electrons, the density of electrons, the drift velocity, etc. This you can figure out, and we will do some examples. So you have here the mobility, drift velocity, the current density, the Hall effect, well, the Hall electric field, dispersion equation, the skin depth, and the conductivity, the DC, the AC, sorry, the AC conductivity. Okay, so this is really what you need. Now, let me also remind you that here, what I'm giving here is epsilon, the permittivity of free space, and the permeability. Now, in some of the applications, I might ask you to do the following. I might ask you to for example, you will see in this problem, I asked you or asked the student at that time, whatever material you use these values, which is not really true, because if you change the material, the permittivity and permeability will not be the same as free space. So normally the epsilon, the permittivity, will become epsilon R, the relative permittivity, times epsilon 0, like we did in 322, in ECEN370, the same thing, the permeability. So in some, please read the question very carefully. Sometimes I will ask you, okay, just use epsilon. This is, by the way, epsilon 0. And some of the times I will tell you, no, actually, for this material, epsilon R is 1.25. So then the real permittivity that you need to include in the calculation is 1.25 times epsilon 0, which is this one. Okay. So let's start the first problem. The first problem is about obviously, you can easily figure it out, is about the Hall effect. I really need you to read, I need you to read the problem very carefully. The figure below shows an experimental setup for a piece of a rectangular conductor. Now, it is a rectangular, it's not I might give you a circular, but it's a rectangular now. Conductor of length L, so length is given, the height is given, and the depth is given. It is mentioned here, the length, the height, and the depth. The conductivity of the conductor is 510 to the power of 7 Siemens per meter. A potential difference, 20 volt, is applied between the faces along the x-axis. The Hall effect is a three-dimension effect. So that's why you need to understand the drawing. The potential difference, here it is just a circuit, a very simple circuit that has a conductor. And that's it. And the potential difference is going across the x-axis. So which means this will create an electric field inside the material. So now, what is the question? First question, now let me read the questions and then we go back to one by one. Again, here, we know that it's an Hall effect, but I still did not talk about the magnetic field. So some students, they started looking, I mean, in the exam, I remember they started using the magnetic field. I did not talk about the magnetic field here. So here, what are the direction and magnitude of the current density of this conductor? Then question B, a magnetic field is applied along the positive direction of the z-axis. Explain what happens to the electrons and identify in the figure the charge accumulation in the respective sides of the conductor. And then the third question, at a steady state situation, a potential difference of 0.1 volt is observed between the phases M and N of the conductor. Calculate the Hall electric field. and then calculate the density of electrons in this conductor. You see, there is the first part, the first question has nothing to do with the Hall effect, just a conductor, you want to calculate the current density, okay? And now the second question, well, the second part, you apply magnetic field, and then there is a Hall effect, and so on. So let's start by the first one. Well, the first one is what are the direction and magnitude of the current density of this conductor? Who can tell me what is the current density? In which direction is the current density? Okay, yeah, so okay, so I think it would be nice to look at the problem. Now, you might say, you will tell me clockwise, but I gave you the axis XYZ. So you need to tell me in which direction. Is it along X, positive X, negative X, positive Y, negative Y, positive Z, negative Z? Okay, okay, very good. It is positive X. Because remember, the current is going this way, and the current is going this way, okay? And the current is going this way. So the J is going this way, okay? So J is going this way. Now, what is the direction and the magnitude of the current density of this conductor? Now, we already defined or decided on the current density, the direction. What is the magnitude? So how do I calculate the magnitude of this current density?
The conductivity times the electric field.
Exactly, conductivity times the electric field. And then now you might argue, okay, well, yeah, that's very good. Okay, I will. So now conductivity is given. Now the electric field. How do I calculate the electric field?
V over L.
Yeah, so it is delta V over the length L. And delta V is 20 volt, right? Divided by delta L is 0.1, right? Right. So the electric field is 200 volt per meter. Okay, and J will be 5 × 10⁻⁷, 5 × 10⁻⁷ times 200. Okay, so this will give you so 5 × 10⁹. What is the unit? Yeah, so the unit is meter. Okay, so this is the question about the magnetic the current density. We still did not talk about the electric the Hall effect or anything else, just the current density for a simple circuit. Yeah, let me tell you, frankly, I have been teaching the whole day. I had a class at 10 a.m. from 10 to 12. I had a class from 2 to 3:30, and now I have a class. So I'm tired. So if I do, you need to watch me because I might be doing mistakes. Okay, so yes, you're right. So it's 10 to the power of 10. Sorry. Thank you, Haya. Okay. Okay. Yes, so let's go to the second question. Again, the second question. So in this kind of questions, please indicate, when you answer, indicate what is happening in the figure itself. A magnetic field is applying along the positive direction of the z-axis. What is required from you? Explain what happens to the electrons and identify in the figure the charge accumulation in the respective sides of the conductor. Now, let's first draw the magnetic field. The magnetic field is along the z-axis. So this is the magnetic field, right? Now, who can tell me where is the drift velocity of the electrons?
Will it be in the negative y?
Exactly. No. I'm telling you the drift velocity. The drift velocity. I still did not. Yeah.
Oh.
So the drift velocity is going this way, negative axis, negative x-axis, because the electron, if you remember, the current is going into this direction, right? And the drift, the drift velocity is opposite, because the electrons are moving in the opposite direction of the conventional direction of the current, right? Now, what do I have? I have this situation. I have a drift velocity going this way along the x-axis, negative x-axis. I have the magnetic field going this way. And I want to calculate the Lorentz force. The Lorentz force, F is equal Q drift velocity cross B. I want to see what is the direction of this Lorentz force. Okay, so you okay, so sometime please, if you exactly don't tell me out of the page or inside the page, because now I gave you the XYZ axis. So I need an answer. So the electrons, you say that the electrons are along the Y axis, okay? Along the negative Y axis. Why? Why do you say that the electrons will be going along the Y, the negative Y axis? Yeah, the negative Y axis, yes, exactly. Yeah. So which is out of the page, yeah. So this means that this phase M will accumulate negative electrons and phase N will accumulate positive electrons, right? Do you all agree? Okay. Okay, very good. So now you understood why it is in this direction. So now, because there is a positive along the y-axis, it's a positive side and the negative side. Obviously, there will be an electric field, a whole electric field created along between the two faces. So the whole electric field will be this way. Okay. Now, what is the next question? At steady state, a potential difference of 0.1 V is observed between the faces M and N of the conductor, of course. Calculate the whole electric field. So the whole electric field is equal to, well, the general definition of the whole electric field of any electric field is the potential difference, which is indicate the whole electric field, divided by the distance. Which distance I should take?
You should take the distance N.
N, which what do you say?
And the distance between the faces.
Yeah, I gave it in the, what is called?
It's called N, right?
No, it is called B.
Oh, sorry, B. I thought N was the distance
No, N
between the
is
faces.
just the name of the phase, and M is the name of the phase,
Yeah.
the other phase. So, okay, so it is called B. Okay, so it is B. And then if I go to B, B is 1 millimeter. So, and the voltage is 0.1 divided by 1 millimeter, which is 10 to the minus 3. Now, please remember, this is the Hall effect. I can tell you many students, they did a big mistake here, is that they put 20 volt, the voltage that is across in the battery, that is across the whole conductor, the whole faces of the conductor, the large length. No, the potential difference that is given here is the whole potential difference. And because we are talking about to calculate the whole electric field, we need to calculate, to use the whole electric voltage or potential difference. And obviously this will give you 10 to the 3, which gives you 100 volt per meter. Yeah. So yes, yeah. Thank you, Haya. You're fast. Okay, so now calculate the density of electrons in this conductor. Calculate the density of electrons. Now, the density of electrons, obviously, we are talking about Ne. So I want to calculate Ne. Any idea? You can look at the formula. What do you mean, question 2? You mean question B? Haya? Yeah, so, okay. Explain what happens to the electrons and identify in the figure the charge accumulation in the... So the first thing is electrons are subject to a force QV cross B, right? This is your question. This is your answer. And then the drift velocity is going this way. The magnetic field is going this way. This means that the electrons will be coming in the negative y-axis. And this will create a negative potential on the M phase and the negative and the positive potential on the N phase. That's your answer. Clear? Yeah, so it depends on, so you want to calculate E. Now, you can do J is equal to NE, E, the drift velocity. But how are you going to calculate the drift velocity? Drift velocity is always complicated to calculate. Now, sometimes you need to understand the sequence of the problem. Well, I gave you this equation as part of the Hall effect. You might try to see if the Hall effect will help you, right? So what did we say? The whole electric field is equal to this formula, right? So the whole electric field is equal to is equal to J times RH times the magnetic field. You have this, you have this, you have this, and this is 1 over NE. So this is equal to J B divided by NE and the electric charge of the electrons. So this means that the number of electrons per volume will be equal to the density that we already calculated, the magnetic field that we got, the Hall effect, which is already we already calculated it, and yeah, and then so I think it was 10 to the power of 10, right? Yeah, 10 to the power of 10. So 10 to the power of 10. The magnetic field is 1.2. The electric Hall is 100 volt. And then the charge of the electron is minus 19. Okay. And I did not do the calculation, honestly, but you can easily calculate it. Let me see. We can do it very quickly. So it's 7.5, 10 to the power of 26 electrons per, so 7.5, 10 to the power of per cubic meter, because everything, we converted everything to cubic meters. Any question? Okay, so what do you want? You want to take a break, or you want to continue 20 minutes and we stop earlier? I would say it's 5:15. Let's stop at 5. We continue now and we stop at 5, let's say 40. Okay, so we'll continue and we'll stop at 5:40. Let me just switch off the light, switch on the light, because I can't see anymore. Okay, so the second question is the second problem. Yeah, so I don't know why. Yeah. Okay. Yeah. So this is the second problem. Let me read the problem, the whole problem. So the electric field of a 2.4 gigahertz wave propagating in a medium along the x-axis can be written as, it's given, where the wave number is given from the dispersion equation. When the conductivity of the medium is 0, calculate the speed of propagation of the wave in the medium, right? Very easy. Now, we now consider the case where the medium is a conductor, large conductivity. In this case, the equation of the wave number has an imaginary part only, and that can be approximated as the inverse of the skin depth. Calculate the skin depth if the medium is silver. And the last question, I think, the last question in this problem, taking the permittivity and permeability as those in vacuum, at which depth does the wave lose 90% of its power? I think it's a very straightforward problem. Let's start from the first part. So the first part is we are talking about the dispersion equations. And if you have the dispersion equations, you can look at the formula dispersion equations. But when the dispersion equation, when sigma, the conductivity of the medium is 0, which is a dielectric, we have seen that it's omega squared mu epsilon. So k squared is equal omega squared mu epsilon. This you can see in the conductivity, in the dispersion equations. This means that k is equal to omega square root of mu epsilon. Now, you can say that, as we did in class, and this is what I would like you to do, is say, okay, 2 pi over lambda, which is k, is equal to 2 pi f square root of mu epsilon. Okay. And then, so it goes 1 over lambda, and the frequency is 1 over t, and then square root of mu epsilon. This means that lambda is equal t divided by mu epsilon, and this means that t times the speed of the wave in this medium. So the speed of the wave is equal to 1 over mu epsilon, and mu epsilon have been given. Okay? A mu epsilon have been given. Again, in this specific problem, in this specific exam, I told them to use the permittivity and permeability of the free space, which is not correct, but I just wanted to make it simple. But you might have, you might be asked to calculate or to use the right permittivity and permeability. This is what I explained before. So this is the speed when the wave, when the wave is traveling through a dielectric. There is no attenuation, and the speed continues as it is. Any question? Okay. Now, we now consider the case where the medium is a conductor. In this case, the equation of the wave number is an imaginary part and can be approximated as the inverse of the skin depth, which means the imaginary part is 1 over the skin depth, okay? The imaginary part, which is omega mu sigma divided by 2. This is the skin depth. And the question was calculate the skin depth. Okay, so the skin depth is equal to 2 omega mu sigma square root. Now, what is 2? What is omega? So mu is given. Mu is the, okay, so please, again, this is because whenever so what is the answer for question 1? Well, yes, we can, let me see here. Yeah, so Cm will be 1 over, what is mu? Mu is 9.8, well, 8.8, it's 9 10 to the power minus 9. So, yeah, so here it will be 884 10 to the power of minus 12 times 4 pi 10 to the power of minus 7, right? Those are the two parameters that I gave, 8.84 10 to the minus 9 and 4 pi 10 to the minus 7, and that's it. And then you do the calculation, 1 over, right? No, you need to solve it. You need to give me, but this is a very straightforward, yeah, so because this you know from physics, the wave number is 2 pi over lambda. You know that the frequency is 1 over, that the frequency is 1 over the period, and you know that lambda, the wavelength of any wave is equal to its period times its speed, okay? Okay, so now in this equation, again, so let's go to the second question. Second question, I already tell you that the imaginary part is the inverse of the skin depth, and I am asking you to calculate the skin depth. The remark I wanted to mention, please, is this is the wave frequency, or the angular frequency of the wave, right? And this is sigma, okay? This is mu. This is the permeability of the material. It has nothing to do with the mobility, because I remember whenever I solve these kind of problems, I remember the mistakes of previous students. And I can tell you that several students, they were asking me, we don't have the mobility. This is not the mobility, this is the permeability, and it is given, 4 pi 10 to the minus 7. So, okay. So let's solve it. So the skin depth will be 2 divided by the frequency, omega is 2 pi times 2.4 10 to the 9, because remember we said that the frequency is 2.4 gigahertz. This is what I gave, okay? Times mu. Mu is 4 pi 10 to the negative 7, and then sigma is given, is 6 10 to the power of 7, and everything squared. Now the unit will be meters, because everything has been in meters. Just do the calculation. I did not do the calculation. Any question? Now, let me, to make it clear, let me also do the calculation so that Okay, so what I find here is maybe you can check, 1.33 micrometers. So it's a very, very small distance, okay? So which means in silver, this wave, after 1.33 micrometers, this wave will lose 63% of its power. Any question? Now, taking the permittivity and permeability as dosing vacuum, at which depth does the wave lose 90% of its power? Now, we know that, let's say, I have, this is the z equals 0 or x equals 0, and this is x at which I have 90% of the loss, which is, which means that if I have P here, which is equal to E0, here I will have, so let's say P0, here I will call it P90, it will be equal to E0 exponential minus the skin depth, which is Z divided by delta, all right, okay? And then this will be equal to 0.1, the initial, because if you lose 90%, what remains is 0.1 or 10%, okay? So, and then all what you have to do is, you know, the ratio of this divided by this. So this means that if you 0.E0 divided by 1 E0 is equal to, so basically let me see. Yeah. So the loss, so you have P0 is equal to E0. And after X distance, you will find 0.1 E0, right? So this means that the ratio between P10 over P0 is equal to 0.1, which is also equal to exponential minus Z over delta. Then you go to ln. So ln of 0.1 is equal to minus Z over delta, which means this Z or X, the dimension, the depth, will be equal to minus delta ln 0.1. Of course, ln 0.1 is P10 or P90. P90, I can call it P90, is when you lose 90% of your power. So then the skin depth, the depth at which you lose 90% is equal to minus delta, which we already calculated. It's minus 1.62, I think, 1.33 microns times ln of 0.1. So you can see that, so ln 0.1, and which is a negative number, times 1.33, this will give you 3.06 micron. So at 3.06 micron, you lose 90% of the power. Did you understand what I did here? Okay. So this is a very straightforward problem. Okay. Any other question? So we'll stop in 10 minutes. Let's do the final one. Again, look, sometimes you are lucky to get an exam like this, or a problem like this one. Problem 3, 30 points. This is a gift, by the way. So in a cube of 1 centimeter side, the effective mass of the electron is 6.10 to the minus 32 kilogram, and the collision time is 0.33 picosecond. Let me talk about the effective mass. By the way, the effective mass, we will see it in chapter 2 later. But I can tell you from now, in the solids, when you do spectroscopy, the mass of the electron, normally the mass of the electron is 9.1 10 to the minus 31 kilogram, right? But when you do spectroscopy in some of solids, we see that the mass of the electron that we have to take into account is not this one, but something called the effective mass. So to be consistent with the reality, I'm giving you the mass of the electron. You don't have to know what is the effective mass, except that the mass of the electron that I want you to use is this one and not this one. In this problem, if I did not ask you, talk to you about the effective mass, you use the 9.1, okay? So now what is so in a cube of solid, 1 centimeter, the effective mass of the electron is 610 to the negative 32 kilograms, and the collision time is 0.33 picosecond. What is the electron mobility? Any answer? Yeah, exactly. Yes, sure. The mobility is equal to the electric charge times the collision time divided by the mass of the electron. Now, 1.610 to the negative 19 times the collision time, which is 0.32. What is picosecond? What is picosecond?
Times 10 to the power of 12.
Okay. Divided by the mass, I gave you the mass, 610 to the minus 32 kilogram. Let me do the calculation. I did not do that. So it yeah. So it's the mobility is 0.88, and the unit of the mobility is meters squared per volt second. Now, a 10 millivolt potential difference is applied between two sides of the cube that generate 14 milliamp. What is the current density? Okay, so J is equal to I over A. Okay, yes. Yeah. And so you get 14 10 to the power of minus 3 divided by the area, and the area is the area of the cube. It's 1 centimeter, so 10 to the minus 2 times 10 to the minus 2. And this will give you your current in meters. Okay, any question? So you see, sometimes you can have a very easy problem. Sometimes you can have, so if you didn't have this, the current, if you didn't have the current, then you would have to calculate the current, or you would have to calculate the sigma, because J is sigma E, okay? And E you have, because you are applying 10 millivolt to 1 centimeter, so you can calculate E, and then you will be probably asked to calculate sigma using the mobility, and if we gave you, for example, the number of electrons. Yeah, okay. Just one last remark. I received a question. What is the difference between the mobility and so this is mobility. What is mobility? Mobility is when you have an electron, the electron is moving. This electron will have a drift velocity. A drift velocity. This electron, by the way, is moving because there is an electric field that is applied. This electron has a drift velocity, and there is a quantity that gives us an idea about how fast the electron can go into this material, and this is equal to the mobility is the proportional factor between the drift velocity and the electric field. This is the mobility. Okay. The permeability, and mobility, by the way, the unit of the mobility is meters per volt second. The permeability is an intrinsic characteristic or parameter for the material that has to do with the magnetic field. Okay, it has to do with the magnetic field. Permeability is a material characteristic or material property that has to do with the magnetic field. And the permeability, we also call it mu, but the unit is in Henry per meter. Is this clear? So there is a difference. Now, what you see, let me give you an example. For example, let me go through some formulas. For example, yeah, for example, conductivity. Conductivity sigma is equal to the mobility here, times Ne, the density of electrons, times the electron field. This is the mobility. However, the skin depth, which is 2 divided by omega mu sigma, here it is the permeability that we should use. Okay, is this clear? Yeah, yes. Okay, thank you. I will stop here and I will send you an email. No, how you can defer. No, you need to just understand the equation. Let me go again through the equations here. For example, I mean, look, this is the mobility. This is mobility. Okay. This is not mobility. This is permeability. Okay. This is permeability. Okay. So I mean, we could have called it anything else. Okay. Okay. So let's stop here, and I will send you an email about the other review session. Thank you.
Professor, will the paper we solved be sent or posted on Canvas?
This paper?
Yeah.
Yeah, I will post this paper. I will post also another exam. Now, on next review session, I will give something a little bit